Next problem. We are given that a car drives around a circular loop at constant speed, and the people in the car notice that the fuzzy dice hanging from the interior mirror make an angle of 35 degrees away from the vertical. Using only those two pieces of information, can we determine the coefficient of static friction between the tires and the road? Now, this problem is an example of one that gives you very minimal information. We are not given the speed of the car, we are not given the mass of the car or the fuzzy dice. So when we encounter a scenario like this, we could write the mass of the car as big M, we could write the mass of the fuzzy dice as little m, and we will just have to work through this problem and trust that at the end of the day, somehow all these terms that we're not given will cancel out. So to begin thinking about this problem, I drew an overhead view of this scenario and a side view of this scenario. So let's draw the forces and the acceleration vectors acting on the car from these two perspectives. If I look at the overhead view, we are told that the car moves in a circle at constant speed. So I know the acceleration vector will point inward towards the center of the circle. I'm going to draw that in. So the acceleration of the car is going to look something like this. Now we could ask what force is responsible for causing that acceleration. Well, let's think of it like this. If you are driving on a road, it is one thing if the road is dry, it's another thing if the road is icy. In the ideal scenario for driving, your tires will grip the road and your tires will not move while they are in contact with the road. And then the tire rolls on itself and that spot on the tire is now gripping the road. If your tire is in contact with the road, but sliding, moving while it's in contact with the road, that's basically your tire skidding. You don't want your tire moving, and that is the coefficient of static friction, as the force of static friction acting on your car in this scenario. If you think about, as another example, when you want to move, when you want to walk, what direction do you push your feet? If you have good rubber-soled shoes on your feet, you push your feet backwards. Your feet are pushing backwards against the floor. Now, if you have rubber-soled shoes on, then there's a very high likelihood that your feet will not slip. They'll just grip the floor very nicely. By Newton's third law, equal and opposite forces, if you are pushing backwards on the floor will be pushing forwards on you, and that is the force that causes you to accelerate forward when you want to move. On the other hand, if you have socks on a wood or linoleum floor, you could slide right across that. You'll have a very low coefficient of friction between your feet and the floor. So this scenario, the tires are going to grip the road, and the friction force, the force of static friction, is what causes this acceleration. So I could draw the friction force to look something like this. Now, there also is gravity and the normal force at play in this problem, but we're not going to draw them on this overhead view, we'll draw them on the side view. So I have gravity pulling the car downward. Here is my force of gravity. And here is the normal force of the road pushing back on the car. Now, if you want to say, well, what about the force of the motor in the car? Shouldn't we be taking that into account? I would respond to that by saying, it is true, the motor does work, the motor does stuff, but the motor causes something to turn, causes something else in the engine to turn. I don't really know how motors work in cars. But at the end of the day, you have the axles that are connected to the tire, and it is the tire pushing on the road, but the force of static friction prevents the tire from moving, but it is that static friction force that causes a car to move at the end of the day. You have a lot of other internal forces going on as well. That's kind of like saying, to make back to our analogy of a person walking, There are forces of muscles pushing on bones, pushing on all these other things. But at the end of the day, I just say my foot is pushing backwards on the floor pushes forward on me, and that's what causes me to move forward. So at this point, the acceleration of the car, the way I drew this picture, is going to be to the left. The car is not going to accelerate in the vertical direction at all. So I am going to set up Newton's second law for these two scenarios and just see what comes up. So for Newton's second law for the side view, I could write F net equals ma, and this is all in the vertical, so I'll say the y direction. Now, the car is not accelerating in the vertical at all, so here this term will be 0. And what are the two forces in the vertical direction? I have the normal force that is pointing upward, so I'll write that as F normal. I have gravity pulling the car downward. The force of gravity is m times g. So I'll write that as minus big M times g. And as we said, this is all equal to 0. Again, I want to be very explicit. We were not given the mass of the car, so we have to trust that somewhere along the way, the mass of the car will cancel out somewhere in this problem. I am specifying the mass of the car as big M because later on in this problem, we're going to talk about what's happening to the dice, and that's a different object. I'm going to specify the dice as having a mass little m. Okay, what's happening to the overhead picture in this scenario? I only have one force acting on the car in the horizontal direction. That is the force of friction that is drawn. So if I want to go with the traditional, to the right is positive x direction, to the left is negative x direction, the force of friction will be in the negative x direction. So I could write minus mu static F normal. There are no other forces to account for. And then equals the mass of the car times negative A. And again, the negative signs are due to all the vectors the way I drew this problem pointing to the left. I could see right away that negative and negative cancel, so I'll just get rid of them without any loss of generality. Now, for this particular problem, we were told that the car is moving in a circle at constant speed. So that means the acceleration for this problem will be v squared over r. So I could write that in. I could write coefficient of static friction times the normal force is equal to big M times v squared over r. Now, from down here, we found that the normal force is equal to mg. So if I want, I could plug this in up here, and I could say coefficient of static friction times big mg equals big M times v squared over r. And like I said before, if you are not given some number like the mass of the car, you have to just work through this problem and trust that these things that you're not given will cancel out nicely. And here we see big M on both sides, so I could cancel them. And at this point, I could write the coefficient of static friction between the tires and the road times the acceleration due to gravity. G is 9.8, but for this problem, I'm just going to write it as G for now. And that's equal to v squared over r. Now, at this point, there is nothing else we could do with these two pictures. So we're going to set this equation aside. We'll look at what's happening to the dice, and hopefully we will be able to get something involving a v squared and an r when we look at what's happening to the dice. And then from there, we could combine these ideas to find this mu s. So let's look at what's happening to the dice next. So I am going to keep this overhead picture here. I am going to keep this equation, I'll just write it off to the side. So I have coefficient of static friction times G equals V squared over R. Now, if I want to draw a picture of the dice, what would we see? Here we have the mirror inside the car. Here is a vertical line. Here is the string that it is connected to the dice. Here are the dice themselves. And we are told that this angle is 35 degrees. Now let us draw the forces acting on the dice. So if I think about what forces are acting on these dice, I know there will be the force of gravity because the dice are on planet Earth. So the force of gravity will pull downward, F gravity. And the dice are connected to a rope, so the rope will produce a tension force. And I know that tension is always in the same direction as the rope, and ropes only pull. So the direction of the tension force on the dice will look something like this. So here I have F tension. I could look at this problem and ask myself, are there any other forces acting on the dice? Well, the dice are not sliding on anything, so there's no friction to speak of. The dice are not placed against a surface, so there's no normal force. So at this point, I've accounted for every force acting on the dice. What I'm going to do next is I'm going to draw these forces on the dice on a traditional XY axis that we are used to. So if I were to draw my X and my Y axes, I'll place the dice at the center. And what are the forces acting on the dice? Well, there is the gravity force pulling the dice straight down. I'll draw that in the negative Y direction. And there is a tension force. The tension force is pointing up and to the left. So the tension force is in the second quadrant. So the tension force will look something like this. Now we could look at this picture of the dice we have here. And if I were to draw a vertical line, just like before, this diagonal line intersects these two vertical lines, and I could say that this angle between the direction of the tension force and the direction of the vertical must also be 35 degrees. So this angle must also be 35, implying this angle is 35 degrees. So now that we drew the forces acting on the dice, I don't really need this picture anymore. Let's think about what's happening in this problem right now. We said there are no other forces acting on the dice, but you can clearly see that F net is going to be non-zero in this problem. Gravity is only in the Y direction. The X component of gravity is 0, but tension has an X component, so there will be a net force in the X direction. So, is there an acceleration in the X direction? You could pause the video, think about it. So what is the resolution to, it clearly looks like there should be an acceleration of the dice because the net force in the X direction is non-zero, but the people in the car do not see the dice as accelerating. The reason for that is the people in the car are accelerating with the dice. If you look at the overhead view to the right, even though the dice move in a circle, the people in the car move with the dice at the exact same rate, at the exact same velocity, exact same acceleration as the dice. So from the perspective of the people in the car, the dice are going to be unaccelerated. But nevertheless, the dice still are accelerating, and the acceleration of the dice will point to the left. So I could draw the acceleration vector on this picture like so. Now, if you want another justification for why we could draw the acceleration vector like this. How about instead of thinking about what the people in the car see, pretend there's a person behind the car just watching this all unfold. And this person looks through the back window and looks at the dice hanging from the mirror. And at the instant the car is right here in its path, the person standing back here behind the car will say there's a downward force of gravity, there's a tension force that is up and to the left, and the dice are accelerating with the car around the loop. The dice will have the exact same acceleration as the car, so the dice will accelerate with a magnitude v squared over r. I could write out the components of these two forces and the acceleration of the dice. The force of gravity will have an x component of 0 and a y component of negative mg. Negative because downward, little m because I'm talking about the dice now. The tension force in the x and the y direction. What can I write about these? I don't know how strong the tension force is, so I will write it in terms of magnitude of tension Ft. And for this particular problem, the way I'm going to break the tension force into its components is I am going to choose to draw a right triangle that looks something like this. Let's say the hypotenuse of this right triangle has a magnitude Ft, and this angle is 35 degrees. Now, if I look at how I drew this right triangle, I could say this side of the right triangle is adjacent to the 35-degree angle. So I could say this will be a side length of Ft cosine 35. And this side of the right triangle is opposite the 35-degree angle. So I could say this side length has a magnitude of Ft sine 35. Now again, when you apply sine and cosine, you begin with the definition of sine and cosine. The opposite side will get the sine, the adjacent side will get the cosine. So now I look at this picture, I look at this vector, and I recognize that this picture looks very similar to that vector. The tension force will have a magnitude of this much, but then I see the tension force is actually pointing in the second quadrant, pointing to the left. So I could write the tension force in the x direction as negative Ft sine 35, and the tension force in the y direction as Ft cos 35. We're setting up this right triangle gave me the size of the tension force in each component, Ft sine 35, Ft cosine 35. After I find the size of those components, I need to then look at this vector and ask what quadrant is this vector in, and that tells me then should these terms be positive or negative. Then I just put on this negative sign by hand. And finally, the acceleration of the dice. The acceleration of the dice are the exact same as the acceleration of the car. In this picture, I could say the acceleration of the dice in the x direction is going to be negative v squared over r, and the acceleration of the dice in the y direction is going to be 0. Here's the acceleration vector entirely pointing in the negative x direction. Now we could set up Newton's second law for F net x and F net y and solve and see what we get. So to do that, let's see. For the x direction, F net x equals max. I could say gravity has a force of 0 in the x direction. Tension has a force that big in the x direction. So I get minus ft sine 35. And that's equal to m times negative v squared over r. Now I could simplify this equation somewhat. I could get rid of the negative signs, and then I could write this as ft sine 35 equals m v squared over r. I'm going to just leave this equation as it's written like this for the moment. Let's set up Newton's second law in the y direction. So in the y direction, Newton's second law would read F net y equals may. So the downward force of gravity, we have minus mg. The upward force of tension, I have plus ft cosine 35. And the acceleration in the y direction in this picture is 0, so all that will be equal to 0. Now, if I want, I am going to rearrange this equation right here to read ft cosine 35 equals little m times g. At this point, we are very close to being done with the problem. Don't worry about being able to see the end result of a problem when you're in the middle of it. Just keep moving forward. Occasionally, if you are not given some piece of information, trust that it will cancel. Just be consistent with everything you do. To demonstrate that, let's look at the three important equations we have right now. We have this equation for the net force on the dice in the y direction. We have this equation that gives us the net force on the dice in the x direction. And we have this equation from way back earlier that we still have to incorporate. So we are not given the tension in the rope. Let's cancel that out. The way I will choose to cancel the tension in the rope is I am going to take this equation and divide it by this equation. What I mean by that is I am going to write F tension sine 35 divided by F tension cosine 35. What is this term going to be equal to? Well, F tension sine 35 is equal to this. So I could then write the upstairs of the right-hand side as mv squared over r. And F tension cosine 35 is equal to this. So I could write the downstairs is equal to mg. When we do this, it turns out not only tension cancels out of this problem, but also the mass of the fuzzy dice cancel out of this problem. And what we're left with is sine over cosine. So I have sine 35 over cosine 35 is equal to v squared over r times g. And sine over cosine is just tangent. So I can write tan 35 equals v squared over rg. So at this point, let's compare what we found just now to what we learned much earlier when we were looking at the motion of the vehicle itself. Earlier, we learned that the coefficient of static friction between the tires and the road, I could bring the gravitational acceleration 9.8 to the right-hand side of this. This could be written as v squared over g times r. And we found from looking at the forces and acceleration of the dice, the tangent of the angle between the dice and the vertical is v squared over rg. So I could compare these two equations and say the coefficient of static friction between the tires and the road is equal to the tangent of the angle between the dice and the vertical. So I get tan 35. And when I put this number then into a calculator, I find that the coefficient of static friction between the tires and the road is going to be 0.7.